If I could have the first slide. I'd like to start with the science objectives for Heimdall. Heimdall is a 4 camera plus DVR imaging system. We have been funded also for CLIPS. Unlike the previous speaker, we were funded not through LPLS, but through LCITIP, which was the first opportunity that was put out to the general scientific community. We were funded in 2019. So there's some long-lived folks out here. Our science objectives are to characterize and map the landing site at multiple overlapping scales, to provide ground truth and support development of autonomous navigation capabilities, to record and model regolith plume interaction, and to characterize the regolith. You'll see I've highlighted record and model regolith plume interaction. We'll be diving into that just a little bit, but if I could have the next slide. I just want to cover a little bit about what some of the other cameras will be doing. We have a panoramic camera that will be doing geologic context. Because it will be mounted on another instrument, the sampler arm provided by Maxar, we will be able to acquire translational stereo imaging as well. And these are the types of images that will allow us to put together a full geologic picture of the landing site. And that will include our descent imager, which I'll be talking about in just a second. So next slide. One of the reasons we have a panoramic imager that can do stereo is to allow us to have some quantifiability in those stereo images to provide real, not analog, local digital elevation models to feed into future traverses and traverse testing. Next slide. We have a regolith imager. The idea here, and again, the regolith imager is mounted on an arm so that we can get close to the surface. The regolith imager will image at about 30 microns per pixel. So we won't get the absolute finest fraction of regolith, but we will get a good fraction of the regolith. And the reason I have a Mars picture here on the right, this is a fragment that's about 30 millimeters long axis. And this is pretty much the resolution that we will achieve, ideally, using the Heimdall regolith imager. Next slide. But I do want to focus on the regolith plume interaction that we hope to capture during descent. So if I could have the next slide, please. Now, I recognize a lot of this has already been talked about, but I also suspect that some folks are having to kind of parachute in and out. So I'll cover very quickly, just a reminder. It's important to understand this interaction between the regolith and a landing plume, both for engineering and science regions. Just to remind you, the impingement of rocket exhaust was significant enough on Apollo to cause regolith particles as large as 10 centimeters or larger to move. And at this size, you can actually, have some damage. That's likely what happened to the Curiosity rover's REMS Boom 1 instrument. It got hit during landing by a small clast. Rocket exhaust also has electrostatic effects that can cause dust levitation up to half a minute after landings. So Heimdall is planned to image the landing plume so we can characterize how much and how far the lunar regolith particles travel. Next slide, please. And one of the reasons this is important is because our best data is Apollo-era descent videos. These are analog, so they're lacking a lot of that quantitative information that really allows us to do modeling that would allow us to calculate optical density and regolith erosion and so on. But more to the point, sometimes with that data, we don't even know the basics like altitude based on image because the altitude was manually called out by the astronauts during their descent. So the idea is to acquire images at not quite 2 images per second, which will allow us to have digital images at known altitudes so that we can feed this information into future models. So next slide, please. All right, I started with the science. Here's the engineering. This is our instrument, and this is, in fact, the Heimdall instrument. It is built and currently in storage. We have 4 cameras. These are color cameras, plus the DVR for image storage. Each has approximately an 80 by 60 degree field of view. What we expect is 500 microns per pixel once we are landed, and approximately 5 millimeters per pixel at 10 meters. And that's 10 meters above coming down vertically, or that's 10 meters out with the panoramic imager. We currently do not have a lander, which is why I have this goofy little cartoon of a lander type object. And this is approximately where we expect our 4 cameras to be mounted. You have the yellow arm there, that's the sampler arm, and you have the panoramic and regolith imagers mounted there. You have the descent imager, the Heimdall descent imager, or Heidi, if you will, mounted at the bottom. And then we have a workspace imager because, again, we have this mobile asset in the sampler arm, and the workspace imager will be pointed at the location where we expect sampler to be doing most of its work. Next slide, please. We have tested our cameras and they are good. Up above, you will see a 360-degree panorama, which I have to tell you for some reason reminds me of one of those old pretentious 70s album covers. But this is the idea of getting a 360-degree panorama of the landing site using the mobility provided by the arm. We expect the drop off of resolution, that is the point where resolution starts to decay a little bit, at about 150 centimeters, 1.5 meters to the target. The actual drop-off point when we tested it was about 25 centimeters to the target. So really excellent behavior by the panoramic imager. Then on the right we have JSC1 in a dark room with a flashlight pointed at it, just to kind of give you an idea of the behavior of the camera under various lighting conditions. And on the left, that's a real world test of the regolith imager with one of those lovely little cards that we geologists carry when we're in the field. That black grain is an angular grain. It's about 16 pixels across in this image, and you can, in fact, when you zoom in, tell that it's angular. So this gives you an idea of the regolith imager's behavior. Next slide, please. We are landing in the Gruithuisen domes. We actually started out, as I said, in 2019. We were task order 19C and then lost our lander, and we have been remanifested with sampler on CP21, which is headed to the Gruithuisen domes. This is a unique and unusual set of higher silica volcanic constructs that are surrounded by Mare material. There are 2 main hypotheses to how these domes were formed. Late stage, that is fractional crystallization at the end of eruptive life, or early stage, that is remelting of high silica crust at the beginning of eruptive life. The issue here is that the first late stage hypothesis requires explaining the older age of the domes, and the second early stage requires the presence of pre-existing granite. And of course, the alternate hypothesis is the null hypothesis. The domes are not genetically related. That is what we hope to approach with landing in this area. So if I could have the next slide, please. We do not have a lander at the moment. We have a number of payloads, including Lunar, and we have been meeting and working on ways to optimize science, both for our own payloads, but among the payloads. And of course, what that means is that we don't know what our ConOps plan is. We don't know what that's going to look like yet. So what you see here is a cartoon based on a number of descent and landing images that I pulled from various lunar missions, and they all approximately looked the same. The idea is you have a lander, you have powered descent initiation, and this is actually a potential opportunity for our descent imager to start imaging. You have vertical descent, and that is the go, no-go for us to start imaging, and then we acquire our final image after landing. The current idea is that we are required, the lander is required to provide us with imaging at approximately 1 to 2 images per second for the last 60 seconds of landing in that video mode. That is a relatively arbitrary number, though, and it's again because we don't know what the landing profile is going to look like. This assumes that dust plume formation starts at approximately 30 meters altitude. Again, a bit of a guess. Single image is going to give some opacity information, but for velocity, really, the video image capture speed is required. Again, deorbit insertion and braking burn or turnover, those are all opportunities to acquire additional images of the landing process. We suspect that what we're probably looking at is additional data acquisition taking the form of a sequence where you get one image every 30 seconds and then maybe every 20 or so, followed by that final command to acquire the last 60 seconds of images in video mode. Just with the last minute here, I'd like to introduce the Heimdall team. That's the next slide. There they are. Hello. An excellent team. I'm really grateful to be working with all of them. One of them is Marie Henderson, who is, I'm sure, virtually waving at this time. And that is all I have. So hopefully I turned back a little time to you. And can I have the last slide? Let's just make sure I've gone through them all. Yes, I have. All right. And thank you very much.